For most of the 20th century, cosmologists assumed something reasonable. The universe began expanding with the Big Bang. Gravity, acting between galaxies, should gradually slow that expansion. The only question was how much. Would expansion slow forever? Would it eventually stop and reverse into collapse? Would it approach zero asymptotically? By the 1990s, astronomers began measuring distant Type Ia supernovae, stellar explosions with consistent intrinsic brightness. These explosions function as standard candles. If you know how bright something truly is, and how bright it appears, you can calculate its distance. Two independent research teams used supernovae to map expansion history. They expected to confirm deceleration. Instead, they found the opposite. The universe was not slowing. It was accelerating. Acceleration is subtle at cosmic scales. It does not mean galaxies visibly speed up in dramatic motion. It means that over billions of years, expansion increases relative to earlier epochs. The data showed distant supernovae were dimmer than expected. Dimmer meant farther away. Farther away meant expansion had stretched space more than predicted. The conclusion required something radical, a repulsive component of energy permeating space. This unknown driver became known as dark energy, not because it absorbs light, but because its nature is unknown. It accounts for roughly 68% of the universe's total energy density, and yet it has never been directly detected. Dark energy is not a force like electromagnetism. It behaves as a property of space itself. One explanation is the cosmological constant, originally introduced by Einstein. If vacuum energy exists, space would possess intrinsic energy density. As the universe expands, more space forms. More space means more vacuum energy. More vacuum energy increases expansion. The feedback loop continues. Another possibility, dynamic scalar fields, or modifications to gravity at large scales. But observations so far align closely with a constant energy density. The problem is scale. Theoretical predictions of vacuum energy exceed observed values by enormous factors. Dark energy is not only mysterious, it is mathematically unsettling. Dark energy cannot be sampled in a lab. It cannot be isolated in detectors. It is inferred from geometry and expansion. To understand it, scientists must measure large-scale galaxy distribution, weak gravitational lensing, baryon acoustic oscillations, supernova redshifts, but existing surveys lack sufficient statistical precision. Small uncertainties blur conclusions. That is where the next-generation instrument enters. The Nancy Grace Roman Space Telescope is designed not to look deeper than Webb. It is designed to look wider. It will survey billions of galaxies. Dark energy cannot be touched, but it can be mapped statistically. The Nancy Grace Roman Space Telescope is often compared to the James Webb Space Telescope, but their missions are fundamentally different. Webb focuses on depth, studying individual galaxies in extraordinary detail. Roman focuses on width. Its wide-field instrument will capture an area of sky roughly 100 times larger than Webb's field of view, in a single exposure, with comparable resolution. Instead of examining a few galaxies closely, Roman will survey billions. This statistical power is essential for cosmology. Dark energy is not a localized phenomenon. It influences structure formation across cosmic scales. To detect its signature, you must measure patterns across enormous volumes of space. Roman is designed to map those patterns with unprecedented uniformity. It will create one of the largest, most detailed cosmic surveys ever conducted. Dark energy affects how matter clusters. Matter distribution bends spacetime. This bending subtly distorts the shapes of background galaxies. This effect is called weak gravitational lensing. The distortions are extremely small, often less than 1%. Individual galaxies are noisy, but when billions are measured statistically, patterns emerge. Roman's high-resolution infrared imaging allows precise shape measurements. By mapping tiny distortions across large areas, scientists can reconstruct the distribution of dark matter. Dark matter distribution reveals how structure grows, and structure growth rate reveals how dark energy influences cosmic expansion. Roman will not see dark energy directly. It will measure its fingerprints in geometry. Shortly after the Big Bang, pressure waves traveled through hot plasma. These waves left imprints in matter distribution. Today, these imprints appear as slight clustering patterns at specific scales, called baryon acoustic oscillations (BAO). By measuring the scale of BAO across different redshifts, Astronomers can track how expansion evolved over time. Roman's wide-field surveys will refine BAO measurements with higher precision. These measurements help constrain the dark energy equation of state parameter, commonly labeled W. If W equals -1, dark energy behaves like a cosmological constant. If W changes over time, new physics may be required. Roman's precision will narrow the uncertainty window. Cosmology is not about single spectacular images. It is about patterns. Roman's survey will measure billions of galaxies across billions of years of cosmic history. Statistical noise decreases as sample size increases. With improved data, scientists can constrain dark energy density more precisely, test whether W changes over time, compare results with supernova surveys, cross-check with cosmic microwave background data. Roman will not announce a dramatic new force overnight. It will refine. And refinement is how cosmology advances. Precision is the instrument. Cosmologists describe dark energy using a parameter called W, the equation of state parameter. If W equals -1, dark energy behaves like a cosmological constant. Its energy density remains constant even as space expands. This scenario leads to continued acceleration. Galaxies beyond our local group will eventually recede beyond the observable horizon. In trillions of years, distant galaxies will disappear from view. The universe will not collapse. It will dilute. Stars will exhaust their fuel. Black holes will slowly evaporate through Hawking radiation. The cosmos will approach thermal equilibrium, often called heat death. This is not explosive. It is gradual isolation. Roman's measurements aim to determine whether W truly equals -1 or deviates. A small deviation changes everything. If Roman finds that W is not exactly -1 and varies, the implications are profound. Dynamic dark energy models propose evolving scalar fields. In some scenarios, acceleration slows in the future. In others, it increases. One extreme case is the Big Rip. If acceleration strengthens indefinitely, gravitationally bound systems could eventually be torn apart. Galaxies, stars, even atoms. Current data does not support this scenario strongly, but uncertainties remain. Roman's improved precision reduces those uncertainties. This is not speculation for drama. It is parameter measurement. Cosmic destiny depends on decimals. Roman will not work alone. Its findings will be compared with cosmic microwave background data, supernova surveys, galaxy redshift catalogs, gravitational lensing studies. If all measurements converge, cosmology strengthens. If discrepancies grow, new physics may be required. Dark energy sits at the intersection of general relativity and quantum field theory. Resolving its nature could reshape fundamental physics. The telescope does not change the universe. It changes uncertainty. And uncertainty defines what we know. Dark energy cannot be seen directly. It has no color, no particle signature, no localized detector signal. Its presence is inferred from geometry. By mapping billions of galaxies, Roman transforms expansion into data. Humanity is measuring not only the past of the universe, but its trajectory. The fate of cosmic structure depends on the behavior of space itself. This is not philosophical. It is observational cosmology. The universe expands. The question is how fast, and whether that speed changes. Roman will not provide spectacle. It will provide precision. And precision determines destiny.